Okay, welcome to today's seminar. Today's speaker is Steve Butler, and he will be speaking about parking functions, which is joint work with Ron Graham and Catherine Young.
So the first part of this is just sort of the basics of parking functions. So if you've seen parking functions before, no surprises. If you haven't, there's some little cute results that are nice to see. And then we're sort of saying, well, what's the essence, you know? What's really going on, and how can we generalize it? And hopefully that will be what I talk to about near the end. Okay. So what are the ideas of parking functions? Well, it's nice to have a picture. So this has something to do with parking. And as you know, parking can be a real hassle. So I'm going to imagine that I have a sequence of spots lined up. You can imagine this, for instance, on a one-way street. I have n parking spots. And so when we start by talking about parking functions, we'll start with parking preferences. And so what happens here is that we have the following. We have n cars and spots. And so far, this is looking pretty promising because simple math says, okay, there's at least as many spots as cars. However, each car has a preferred spot. So in other words, some people say, I like to park near the front, I like to park near the back, and so forth and so on. Now, the problem, of course, is that some people might prefer the same spot, and so we can't have two cars parking in the same spot. Now, what happens? So, cars enter one at a time, and if you want, we can talk about two variations. There's the cars are ordered, or the cars are unordered. We'll look into both. Cars enter one at a time, and they go to their spot. Okay, that seems fairly reasonable. Two things can happen. One is they can park. Spots available. So, spots available, they park. Well, what's the other option? The other option, well, the spot's not available. So they start moving towards the exit. So again, I'm marking this by arrows to indicate 1, then 2, then 3, then 4. So spot is not available, move to the exit, and park as soon as you can. So park in first available spot. Now, you might say, well, hold on a second. What if you can park? Absolutely right. So if you get to the end without parking, you just exit and you give up. All right, no shopping trip that day. All right, so that's the idea of parking preferences. Now, what's a parking function? So a parking function, that's going to be a parking preference where everybody parks. So that's the idea of a parking function. So nobody exits, everybody's happy. Well, maybe they're not happy because they didn't get their preferred spot, but at least they got to park. So let's try to do some examples and see what we can say. So suppose I have, like I have here, 1, 2, 3, 4. Well, what's an obvious parking function? If I have the 4 cars, car 1, car 2, car 3, car 4, well, any permutation of 1, 2, 3, 4 will work because everybody has their own spot. There's no competition. It doesn't matter. So I can do 3, 4, 2, 1. I can do anything. Okay, so those are parking functions. Are those the only ones that matter? Are those the only ones that are possible?
1, 1, 1, 1, 1.
Okay. All right. So you can. This is sort of an extreme case. Is 1, 1, 1, 1, 1. Okay, as suggested by a random member of our audience. Now, what does this happen? Well, the first car goes to 1, and they park. That's great. The second car comes in, tries to park 1. Ah, too bad. Spot's already taken. Goes to 2. So then, after 2 rounds, the first 2 are taken. Third car comes in. Nope. Nope. Aha! Success. Okay. The fourth round. Nope. 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 Ah, but I can still get there. Okay, good. So that's good. All right. Well, there are, of course, lots of other variations. You could do 1, 1, 2, 4, and some various things. We'll talk a little bit about how you count these things. In fact, let's count these. So it's a nice fact, and I'm going to emphasize these are ordered parking functions. So in other words, I'm going to think of the 1, 2, 3, 4 as being distinct from 3, 4, 2, 1. So even though the same set of spots are preferred, I'm going to take into consideration order of matters.
I have a question.
Sure.
So let's say car prefers, the car 3 prefers 3, they drive up, they do park at 3, right? They know immediately who's open and who's not, I guess is the idea.
Well, initially, you can think of this as going into a blind alley. So you don't know what spot is open, but you know that you really have your heart set on that one particular spot.
Okay.
So you go to that regardless of what else has already happened.
Okay. Suppose they choose 4, 4, 4, 4.
Yes. So one person will park and the rest will all exit and they just give up.
Okay.
It's a very sad situation. Very, very troubling.
No reversing.
No reversal, yeah, yes. One-way streets. One way. And
This is
that's
lot 5
gonna be-
essentially.
Well, you know, I don't park on campus, so I don't know.
Okay.
But I can believe that there are probably many places where this is how parking works. So, how many ordered parking functions are there? Well, this is going to depend on n, and the answer is very nice, n plus 1 to the power n minus 1. Now, you see something like that, and if you're in a, say, for instance, a discrete math kind of mindset, you might be someone who goes to a discrete math seminar. Okay, say n plus 1 to the power n minus 1. Where do I see those kinds of numbers? And they show up. Does anybody know?
Label tree.
Yeah, the number of label trees on n vertices. Of course, that's not the only thing that they are. So those kinds of numbers, they make mathematicians excited. Not as excited as when we get to the unordered ones, but at least that makes a mathematician very excited. So we're going to talk about a proof. Now this is kind of an interesting proof. So here's the picture. I'm going to think instead of having it on a one-way street, I'm going to have the cars go on a circular route. So 1, 2, 3, and there's the nth spot, and then there's a special spot, and it goes back across. Okay, so 1, 2, 3, and so there's a total of n plus 1 spots now. The game still works as before. The n cars each have their preferred location. They each go to their first preferred spot, and then they follow the arrows until they can park. It's okay if they wrap around. All right. So let's make a couple observations. Observation number 1, everybody parks. Okay, that's pretty obvious. Because there's n plus 1 spots, there's n cars, you're going to be guaranteed to get a parking spot. Okay. So this is good. So I know that everyone parks. Well, let's be a little bit more precise here.
So, Steve,
Yes.
they can park on the spot.
You can
with
park
star.
on the star, absolutely.
Okay.
In fact, that's going to be important here.
Yes, it will be those that
In just a second. How many functions are there here? How many preferences can you have? Well, there are n cars, and how many spots can they choose? And yes, you can choose the star. How many can you choose? Well, n plus 1 to the nth power, because each one picks one of n plus 1 options. So there's the number of preferences, and this includes with star. That's equal to n plus 1 to the nth power. Now, we're just going to make a quick observation. How do I know if I have an actual parking function in this setting? Well, two things have to be true. Nobody has to prefer the star, and nobody had to exit. So in fact, I'll have a parking function as long as that one's not covered. And if that one's not covered, then I also have a parking function. So the number of parking functions you want to count how many times the star is not used. Now, here's the beautiful part. This is symmetrical. So this spot is as likely to not be used as any other spot. So what's the probability that we don't use that spot? 1 over n plus plus 1. There are n plus 1 spots, so the probability that we don't use any one particular spot is 1 over n plus 1. And therefore, what we do is we take the total number of these preferences, n plus 1 to the n, and divide it by n plus 1, and we get n plus 1 to the n minus 1. That's the number of parking functions that there are. Now, this proof is attributed to Pollock. Now, why is it attributed to Pollock? Well, because there was a book written by John Reardon who said, this is Pollock's proof. But Pollock didn't do this kind of stuff. So who came up with this proof? Well, we don't know for sure. We know it came out of Bell Labs. Some people said that Ron Graham came up with this. He doesn't know. It's so long ago he forgot. It wouldn't surprise him. But it's one of these great books, you know, it's sort of almost like an apocryphal proof. Who came up with this proof? I don't know. We'll never know. But it's a nice, beautiful proof. Okay, so these are nice numbers, but I want to talk about something a little bit different. So I want to talk about the number of unordered parking functions. So let me be a little bit clear about what I mean by that. I really mean I don't care the relative ordering of the preferences. So, which is strange because now I'm going to say order but okay. So previously I thought 1, 2, 3, 4 and 3, 4, 2, 1, these are distinct. Now I'm going to think of them as being the same. Because there's one car that prefers 1, there's one car that prefers 2. There's one car that prefers 3, and there's one car that prefers 4. Fun fact, we won't do the proof, but it's not a particularly hard thing to see, especially if you just sit there and think about it for a while. It doesn't matter which order the cars come in as to whether or not you'll succeed in parking all of them. So if one ordering gets everybody parked, another ordering gets everybody parked. Okay. So now, a quick question. What needs to be true? Well, if we look at this picture, we can make some simple observations for at least this case, and then we can generalize pretty quickly. If I want somebody to park in spot 1, what needs to be true? Someone has to prefer spot 1. Because if everybody prefers spot 2 through 4, you'll never park in spot 1. Now, how many people need to prefer spot 1? At least 1. Okay, so I need at least one person to prefer spot 1. Okay, this is not a very profound observation, but let's build off of this. Suppose I say, how many people need to prefer spot 1 or spot 2?
2 or more.
2 or more. Now, why do I need 2 or more? Well, suppose I had less than 2, then everybody else would be parking on that side. So if I had less than 2, I'd have less than 2 cars that could possibly park here, which means I'd have to have an open space. In general, if I have a whole bunch of spaces, and so I mark this by starting using symbols here, if I say, how many cars have to prefer the first I spots? What's the answer? I or more. So we need to have, for unordered parking functions, it's necessary and sufficient, which is nice, to have at least I cars preferring spots 1 up to I. This is for all I. So it's not so hard to see that it's necessary. It's also not so hard to see if it's sufficient. If at least one car prefers spot 1, you know it can park. If at least 2 cars prefer spot 1 or 2, well, you know at least one is already parked there. So you know there's going to be at least one car available to park in spot 2, and then so forth and so on. So how do we translate this? Well, what do I mean by translate this? We had this nice proof of n plus 1 to the n minus 1. Let's see, I have to remember what erasers work with what word. There we go. I can mark this now in a nice sort of framework. Let's come up with a parking function just to illustrate, because I think illustrations are really useful. Let's not go too crazy. Let's suppose I have a parking function on 7. So I have 7 slots. All right, so unordered, so we'll start with the smallest, go up to the largest. So does everybody have a favorite parking function on 7? Okay, all that's okay. You don't have to have a favorite. I don't blame you. I know how you feel. So suppose I claim that, let's see, 1, 2, 3, 4, 5, 6, 7. Okay, there we go. I claim this works. And you can check. At least one car prefers 1, and at least 2 cars prefer 1 or 2, and so forth and so on. It's not so hard to verify. But what I want to do is I want to draw the picture, and the picture is much more insightful. So I'm going to draw a grid. This is going to have 7 lines, 7, that's 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. And now what I'm going to do is I'm going to mark points. So I'm going to mark a pair I, comma, number of cars that prefer spots up to I. Okay, so where's my first point? So 1, comma, 4. Okay, so 1, 2, 3, 4. So I think I'm going to mark this right. There we go. 2, comma, 4. 3, comma, 5. Okay. 4, comma, 5. Let's see, have I done this right? Let's see, 1, 2, yeah, 3. Let's see, I think the next one should be here. So this is 1, 2, 3, 4. Then 5 is going to go up. 6 is going to go up, and I'm going to end up here. All right. Now, here's the nice observation. This is when I wish I grabbed my colored chalk, but I did not grab my colored chalk. How do I know if I'm going to, oh, wow, but is it colored?
It's the cheap stuff.
Okay, so the good news is that if you miss this talk, it's going to be on the board for the next 3 weeks until they're able to erase the cheap colored chalk. Here's the beautiful observation. If I'm going to be a valid unordered parking function, I cannot get a point down here. If I'm at a point down here, then I don't have enough cars to fill in those first I spots. And therefore, I can now translate this, think about this as a nice walk on the lattice, which stays above this line Y equals X. And here's the really cool part. These lattice walks are nice numbers. Does anybody know how many walks there are if this is n?
N, 1 over n, and 2 n choose n.
Ooh, that's close.
Little bit.
But
N plus
what's the
1.
name?
Catalan number.
These are Catalan numbers. These are the Catalan numbers. That's why I suspect strongly that people love parking functions, because they love Catalan numbers. If I'd thought ahead of time, I would have brought over my Catalan numbers book by Richard Stanley. So Richard Stanley, who wrote the book on enumerative combinatorics, he actually wrote 2 books, and enumerative combinatorics volumes 1 and 2. So he has this wonderful book that goes through and gives, I don't know how many interpretations, over 100 different interpretations of Catalan numbers. And so among them is it's the number of walks on the lattice here that go from this corner, 1, 1 to the corner n, and always stay above the line y equals x. Well, it's also the number of unordered parking functions. And of course, once you have the Catalan number showing up, then you have 100 things you can connect it to. And so you have all these fun things that you can do.
Do you want to name the paths that do that?
Well, okay, I have to be careful because any way you pronounce this, you'll probably make somebody feel embarrassed. So I've heard this pronounced in 2 different ways. So Dick Pass or Dike Pass. And so either way, you'll have somebody who'll say, oh, okay, I know what you're talking about. I don't know what the correct pronunciation is.
I don't know either. I assume it's Dutch, but I don't know.
Yeah, so assuming it's Dutch, then dike is probably the right word. But,
I thought you mean Dutch paths.
Dutch path? No, not quite those. Now, I will say there are lots of variations of this, so if any of you ever studied what's called Q analogs, so the idea of Q analogs is you want to refine your count a little bit more. So you're not only counting parking functions, but you're counting parking functions which have certain properties. So it's sort of a refinement process. I shouldn't say it sort of is. It is a refinement process. And if you're interested in Q analogs, there's a nice one for parking functions, where what you count is how many times did a car get to a spot and say, dang it, somebody's in my spot. You know, if you count how many times that happens, then that becomes a Q analog, and that's been studied before. Now, this is all classical. A few years ago, Catherine Yan came to visit Ron Graham, and I just happened to also be visiting Ron Graham. He has a wonderful basement to visit him in, and so it's, you know, not many basements get an ocean view, but his does. So I was visiting, and Catherine came in, and she said, I have this interesting idea. Let's think about what parking functions are. So we're used to thinking of parking functions in terms of this one-way street. But I've drawn it in a slightly different way. I've drawn it as this path here. Okay, so what's important about a parking function? Well, in my mind, there's two key elements to parking functions. Number one, cars have a preferred spot. Okay, now that's really, anybody can do anything with that. Number two is what to do when they get to their preferred spot. Well, you either park, and if you can't park, you need to do something. And now we can rephrase this by the following. If we think of this as the route of our path, we can do the interpretation that cars try to park. Now, if they can't, then they move to the route. Now here we're relying on the fact that in the path there's only one way to move to the route. And they park as soon as they can. And if they can't park, then they exit. Otherwise, exit at the route. So we said, okay, well this is great. So really, what we have here is we have this lovely idea applied to a path, but paths aren't the only thing where there's a unique way to go, move towards a certain vertex. In fact, there's a wonderful, nice subject called trees. So trees are graphs. There's lots of ways to define trees. But for me, I like the following definition. There's a unique path between any pair of vertices. So I can take any single pair, I always have a unique path. So I'm really interested in rooted trees. So I'm going to talk about parking functions on rooted trees. Now, oops, trees. So I might have some very complicated parking garage structure, such as that one right there. Now, first question is, how many are there? We actually don't have a great way to say, you give me an arbitrary tree. Now, we have a fantastic way to do that, but we don't have a nice theoretical result that says, you give me a tree with some various parameters, and I can tell you from the parameters what's going to go on. You know, it's subtle. Even with the path, the answer turns out to be Catalan numbers. Now, for instance, if I take this very small graph here, and I label things, so 1, 2, 3, 4, and 5, how many parking functions would there be on this one? If I think unordered, so I don't care about order. Any guesses? So I don't have to guess, I have a cheat sheet. Now it turns out that for this graph,
So you need someone to prefer every single route.
well, every leaf.
Every leaf.
Right. So there has to be at least one car that prefers 1, one car that prefers 2, one car that prefers 3. That's absolutely true, yes. So that's a limitation. So particularly if you have a lot of leaves, that definitely puts a limit on what's possible. It turns out that this has 12 different parking functions. I won't go through and write them all down, but you can. It's not too hard. It wouldn't take you very long. A good warm-up exercise. So, this is nice, but, these are small. And initially, the way we had to count parking functions was really bad, which was we said, okay, let's look at every single possible parking preference. Let's see which ones work, and then we'll add them all up. That's very inefficient. You don't want to do that. Because, once you start hitting 10 vertices, it takes a really long time to do that. And so we said, well, what can we do? So to sort of get a flavor of what our approach is to trying to count these things, is let's think of a very special case. Suppose I have my root vertex is V. This is my root, you can tell because I wrote root right there. And it has above it two subtrees, T1 and T2. And so my picture is a nice root with two things going up. Suppose I want to count the number of parking functions in this big tree here. Well, naturally, you would say it must depend on how many parking functions there are for T1 and T2. But there is some subtlety. So how can I create a parking function in this case? There are three different ways I could form a parking function. So let's, for reasons which will become clear in just a moment, I'm going to let P0 of Ti, that'll be the number of parking functions on that tree. And unfortunately, just knowing that number is not enough. Okay. I'm also going to let P1 of Ti be the number of parking preferences on Ti where all spots are filled. So every vertex gets a car and one car exits. Okay, so in particular, if I had 5 vertices, there were 6 cars that tried to park there. All the spots got filled, but one car, there's not enough spots, so it had to go out unparked. So suppose I know that information for both T1 and T2. Do I have enough now to figure out how many parking functions there are on the combination? The answer is yes, of course. That's a big build-up to say, we still don't know. We still don't know. And why? Well, because there are 3 things that can happen. Either we have a nice parking function up here, a nice parking function up here, and there's one car that prefers the root. So there's a car that actually has the root as a preferred vertex. So how many ways are there to park? How many parking functions are there?
T1 times T2.
All right, well, P0 of T1, P0, so I can take P0, T1, P0, T2. So this is, some car prefers the root. But I don't have to have a car that prefers the root. We saw, for example, as Dr. Legitsky pointed out, 1111, that parks here, but nobody preferred the root of 4. So what might happen is that that car that ends up parked at the root might have come from somewhere else. So there's 2 somewhere else's it could come from. So if it came from T1, well, I had to have one car exit T1, no car exiting T2. Or if it came from T2, I had to have no cars exiting T1. I looked at that and said, wow, that's really cool. That's a great idea. But you know what? We need to go deeper. We need to count more. And this is one of those times when counting more makes things easier. It sounds strange and it sounds completely contradictory, but let me try to convince you that it works. Or at least give you a sketch of what I mean. So the notation is hopefully suggestive that I'm going to do something a little bit different and try to generalize. So instead of just keeping track of how many functions there are no car exits, how many there are one car exits, I'm going to come up with the following count. I want to count P sub I of T, where this is the number of parking preferences where every vertex It's a car, and I cars exit. Okay. So in particular, there's a lot more extra cars. There's I more cars than there are vertices trying to park in this street. So I want to understand this count. So now I'm not trying to count just the number of parking functions. Our real goal is we want P0 of t. But the way we're going to do it is we're going to find all of them. Okay, so how can we possibly find all of them? Well, we need two things. We need to figure out what happens for some tree. So I'm going to pick a tree which is not too bad. Single vertex. That's a tree. What can I say is pi of this tree?
The indicator function for I being 1.
Well, it's literally always 1. This is nice. That's the tree that we can do without any hard work. Okay, but it seems like we're not enough, and there's one more key ingredient here. I want to combine all of these pieces together into one single object. And whenever you have a nice index, such as an I, there's an obvious way to do this. And that's what's done by generating functions. So this is not too surprising. As soon as you see an index, you should think, there's probably a generating function about to show up here. And so I'm going to have a polynomial p, which is a function of x, and it's going to be the sum of everything greater than or equal to 0 of this coefficient piece of I of t, x to the I. So I'm a descendant, academically, of Herb Will, who wrote the book Generating Functionology, which is a book about generating functions. And so I'm a big believer in using generating functions when you can. It's in my blood, you know. It's in my blood. And so what are we going to do? Well, how do you think of generating functions, by the way? Really what you're doing is it's a list of coefficients. This power of xi is just a convenient way to help separate things. But it's a long list. It's a sequence of numbers. If I come back to this example, what do I have? Well, I have p of the vertex, the single vertex tree of x. What does that become? Well, it's the sum k greater than or equal to 0 of 1 x to the I. Now this happens to be a function which we know. This is
1 over 1 minus x.
Yeah, it's the geometric sum. So it's the geometric sum. This is what you guys will get to do when you teach the calc 2. All those calc students love the geometrics. It's like the only series we really know how to do. 1 over 1 minus x. Now, here's the fun fact. And I'm not going to prove this because I need to finish early. But we need to have a starting point. And here's a starting point. Now, here's the fun thing. Suppose my graph has the following structure. So it has a root, and I have T1, T2, up through T sub k. So I have k trees going off of this one single root. Then, the polynomial, the generating function pt of x, is equal to 1 over x times the product over all I of the individual generating functions for each one of these trees, divided by 1 minus x, and then minus the product of all these trees evaluated at 0. So that's the result. Now, what is this saying here? It says that if I know the generating function for these subtrees, I can find the generating function for the bigger tree. But I also know the generating function for a single vertex. And so if I combine those two, what I can do is I can get a nice recursive way to generate any tree I want. In fact, we've implemented this in Sage, which is not a very fast program. And we feed it in a tree on 100 vertices, faster than we can hit the enter key, it spits out the answer. And it's this gigantic, huge number, ridiculous huge number. This recursive way is super efficient. It actually does really, really well. I suppose since I have maybe 2 minutes, I'll tell you why this is true. And I won't fill in every detail. It's an interesting exercise left to the audience. Or you can just come find me. And this paper should be posted sometime in the next week or two on my papers list, so you can find it in there. It really comes down to just thinking about what's going to happen. Because let's write down a basic formula. If you can understand this formula, then the rest of the proof is pretty straightforward manipulation of generating functions. So if I want to count how many ways there are to park with n cars exiting my tree here. So this, when I say t, this is what I'm calling t. So if I want to count that, that's equal to the sum, j equals 0 to n plus 1 of, the sum m1, m2, up through mk. I'll explain what that notation means in a second here. Of the product, I equals 1 to k, p, m sub I, t sub I. Now this looks like a horrendous mess, but I want to assure you, it's not a horrendous mess once you understand what everything represents. So what I'm talking about here, this is an ordered partition of j. So in other words, I'm splitting j up into pieces. And I can't spell partition apparently. I should come up with a different word. So I want to say, how can I write j as a sum of k things? Some k non-negative terms. So what is j? J is an index. I'm going from 0 to n plus 1. Now, what's that special there? Okay, n cars are going to exit. How many cars can prefer the route if I have n cars exiting? I should say, I might have no cars preferring the route because they may all come down from above. What's the largest number of cars that can prefer the route?
n plus 1.
N plus 1. He cheated. He looked at this index right here. Why n plus 1? Well, if you had n plus 2 cars that prefer the route, remember, only one car gets to park there. So if there's n plus 2 cars that like that, at least n plus 1 cars are going to exit. So what this right here, this index here, j, that is how many cars prefer the route. Or let's see. Actually, the way I'm doing it is how many cars don't prefer the route. That's the way I'm actually doing that. No, wait, no, okay. It's related to how many cars prefer the route. Okay, that's how I have my notations that I got. But so I just need to know how many cars. Oh yeah, no, I was right. How many cars prefer the route? Yeah, how many prefer route? Well, okay, we'll fix this later. All right. If I know how many prefer the route, then I just have to figure out, okay, I think that's just like well. I just need to say, okay, how many are coming out from not the route? And so this is what this is trying to do. So I think this is the wrong thing. This should be it. So how many are not coming from the route? So that's what I'm after. So if I know how many are not coming from the route, well, where are they coming from? They're coming from somewhere up here. So I need to know how many come from the first tree, how many come from the second tree, so forth and so on. So that's what this ordered partition is telling me. And now if I know how many are coming from each one of those trees, I know what the right count is for each one of those trees. And I multiply them all together, I add up over all the possibilities, and I get the result. And then anyways, from here, the rest of it is generating functionality, which is a great book. And I think I'm going to stop here just due to time constraints. So, all right, thank you.
Any quick question for Steve?
Yes, part 2, lattice paths, will be another day.
Are there any natural situations in which this polynomial is invariant, under which vertex you choose as the root?
Not that we know of. So what we've done is we have run this polynomial on all trees up through 18 vertices, and it's always been distinct.
For each, the set of polynomials, is that what you said?
Well, so if I look at any tree up through 18 vertices, just that collection of trees, no polynomial is repeated. So no generating function is the same generating function for two different trees. And so when I say two different trees, I mean two different rooted trees. So changing the location of the root changes the number of parking functions there are. Now, you know, there's lots of interesting things. We know very little about this. We basically can do some very simple counting, and lattice walks we can relate back to very particular types of trees which are called caterpillars, but that's a different talk. So.
And also, are there any interesting conjectures related to this statistic?
Not that I know of, but this is very, very
You
young.
wrote the paper, so.
Yes. Well, the one conjecture I'm really interested in is it unique? So if you give me the generating function, will you always be able to reconstruct the tree? We actually have a method. So once you have this recursion, it actually tells you how to reconstruct almost the tree. When I say almost the tree, it depends on whether or not you can have a factorization in two ways that produces the same polynomial. We haven't ruled that out. But if you give me a polynomial, I can actually reconstruct the tree that it came from. Or I should say, I can give you a tree that produced it. You have to be patient with me, it would take me a while, but I could do it. I have the technology.
Other questions? Let's thank Steve again.
Next week,